Hello everyone, my name is Gideon Kaempfer, or Gidi, short, head of core engineering at StarkWare, and I'm here to talk to you about the wonderful world of L3s. So, I'll talk a little bit about what apps want, what they require for their deployment, a little about the layered approach. Everyone here is obviously aware of layer 2, but we'll talk about the basics and how that extends. We'll extend it through recursion, and then we'll talk about the wonderful world of L3s. So what does an application want? Well, different apps need different things, and I call them appetites. So some apps care about privacy, some apps care about performance. Maybe performance means 1 transaction per second, maybe it means 10 transactions per second, maybe even more. Some apps don't care about other apps. They want to be on a centralized platform, or they want to be on a decentralized platform. Some apps are very sensitive to congestion, or to fees, or to deterministic performance. Others don't care that much. And according to all of these requirements, different apps will choose different platforms. And I'm here to talk to you about choice, not about one solution that addresses everything. Some apps are suitable for layer 1, for layer 2, for layer 3, for different kinds of layer 3s. So we'll talk about that. And as we progress, the more they can get, these apps grow their appetites. It was attributed to Bill Gates, although I think he said he didn't say it, that 640 kilobytes should be enough for anybody. Well, I know it in different versions, like a 40 megabyte hard drive should be enough for everyone, megabyte, not gigabyte. But eventually, as you know, the more that gets offered, the more the apps will consume. So it's not just a matter of building a scalable platform, for instance, it's also a matter of which apps will consume that. Eventually, everything will become congested. Eventually, there's always a need for more. So let's talk about the basics of layering, what the whole idea is about. So everything began with the blockchain. Layer 1. Layer 1 is public, it's decentralized, it's secure, but it's slow because all the computation on layer 1 is repeated, meaning every validator needs to recompute the transactions and validate they're okay. As a result, it's congested, because it's slow to operate, and the more apps consume, the more congestion is created. And because there's a trade-off between the need to get on a chain and the performance, it becomes expensive. And that's what L2s are here to solve, right? So the app goes up to L2. And in order to make L2 offer what you need, you want to track its state on L1, and you want to make sure it's secure. And that's done through a verifier contract on L1. And the benefit of L2s is basically that it becomes much faster, because there's no repeated computation, but there could be a single sequencer building the blocks, and everyone else only needs to verify the validity of those blocks, or in this case, the layer 1 verifies the proofs sent to layer 1. As a result, there's more capacity, there's lower cost, less congestion. And it's as secure as layer 1 through these proofs. Layer 2 can be app optimized, can be centralized, can be private, or it can be a public, decentralized platform like StarkNet. In an app optimized case is StarkX, for instance. So that's the basics of layer 1, layer 2. And now enter recursion. I know there were a couple of talks mentioning recursion already today, but I'll quickly jump through the slides and describe the basics of how recursion works. So we have a program, a statement that we want to prove. Basically, the statement is a transaction on layer 2 is correct, and we want to prove that to layer 1, right? That's the typical case. So until now, we proved program execution just by sending a proof to the verifier, and then the verifier verified the proof. But because we use a language to express those statements, Cairo, we can also use that same language to build a program that verifies proofs. And then we can actually prove the verification of a proof. Oh, now it becomes a little bit more tricky. And we can verify that verification. So bottom line, we did a verification of a proof of a verification. Now, this doesn't seem too interesting because we could repeat this forever, and what do we gain? Well, this is the critical point. We can actually even prove multiple verifier programs verify the proof correctly. And then we can verify that double verification. Now, the 2-to-1 here is the essence of recursion. So if we apply this pattern again and again, now we gain. Because every time we compress two proofs into a single proof. And if we repeat that many times, we can do that in parallel, we can do that in any form of binary tree that you like. We end up in proving in one proof many, many statements. And that's the essence of recursion. So I was told this audience is techie. So I was asked to give some technical anecdotes about recursion. It's to make things interesting, okay? I know the real guys that are technically oriented, they're now at Shachar Papini's talk talking about Sierra, which I highly recommend, by the way. I should have said that in the beginning, but never mind. But let's talk about some interesting tech stuff about recursion. So there are actually quite interesting trade-offs to be made between the prover and the verifier in this context. Why is this different than the regular proof versus verifier kind of situation? Normally, a prover works quite hard to produce a proof, and we're not so motivated to have the verifier more easily. Since verification is considered an easy job, right? We do it in logarithmic time of the prover, so what do we care about? Of course, that's a lie because we care about gas consumption, we care about number of queries and all kinds of things, and hash functions maybe. But in recursion, something really cool happens because we prove the verification of a proof. So simultaneously, when we change the proving algorithm, we're both changing maybe the performance of the prover and the verifier simultaneously, affecting the same execution of an implementation, if you like. Okay, so for instance, let's say I decide to do Merkle commitments using a given hash function, which is very x86 favorable. Okay, so maybe a SHA-2 hash function. So as you know, in Ethereum, SHA-2 is more costly than Ketchak. Same goes for a Cairo verifier. Certain hash functions are more expensive than others. So let's say we choose to do everything. Originally, we would prove to Ethereum, so we do all the Merkle commitments with a Ketchak hash function. Verifying Ketchak in Cairo is very expensive when compared to other hash functions. So though we can get a very quick prover in terms of the proving aspect, when we want to prove a verification using many Ketchak hashes, the trace of the verification grows significantly, and as a result, the proving time also increases. So although we've optimized the prover, we actually degraded the performance of the verifier and hence the performance of the prover. So these kind of challenges exist. So here we can play around with interesting things like combining different kind of hashes for different kind of parts of the proof. And as a result, we get interesting effects on the time it takes to prove. That's one aspect of recursion that becomes slightly more challenging than the normal prover-verifier aspect of things. The other aspect, which is also interesting, is that if you look at the recursion tree, so let's assume you have many, many statements that you all want to prove into one large proof or one recursive proof. And this is like, think of a binary tree with many leaves and a root at the bottom, or if you like to build it up from the bottom up, that's also okay. Not all nodes in this tree have to be identical. So maybe certain leaves will use some version of the prover and produce a proof, and then other nodes in this tree will use a different version of this prover, of maybe using a different trade-offs, different built-ins, if you like, in terms of Cairo, different hash functions. And as a result, we can get all kinds of interesting things. So for instance, we can actually hide from the root verifier, the one that actually the proof that gets submitted on chain. We can hide all kinds of fancy things in the Cairo language that are needed for the leaves, for the basic statements written in Cairo. So for instance, in our upcoming version of Sharp, which is our shared proving service that's used today by StarkNet and all the StarkX systems, we will be supporting Ketchuk in the leaves as a built-in in Cairo. But the verifier on Ethereum that actually verifies proofs doesn't support that built-in. So different nodes in the tree will have different support without touching anything having to do with the soundness of the proofs or anything of that kind. So we can optimize for different parts in the tree, different locations. And there's room for lots of creativity, and we're continuing to innovate, introducing more efficient hash functions, trading off between different hash functions in the same commitments, and various other aspects. So that was the part about the cool stuff in technology of recursion. Let's talk about the benefits. Okay, business. Well, it's trivial. We reduce gas cost per Cairo step, statement, whatever parameter you want to look at. We use one proof on chain for a growing number of statements or a growing number of Cairo steps. Today we're at about 2 billion Cairo steps max in a single proof. But it's not a theoretical limit. In fact, we could go significantly higher than that. It's just a matter of trading that off versus the latency of submitting proofs on chain. And typically, that's a matter of UX of the various applications. StarkNet wants L1 finalization within X time. StarkX systems, trading systems, maybe want to have that finalization in a longer time or shorter time, and we can trade that off versus the size of the recursive tree. But clearly, large proofs, lower cost. It also reduces latency, since there's no need to run one single prover once you get all the transactions, create a huge proof, and then submit it on chain. We can actually begin proving as soon as there are enough transactions coming in for a small proof, a small leaf, and already begin. And in fact, we can run many, many provers in parallel, since if you depict in your eyes a binary tree, there are many, many nodes that are independent. You can run them separately. So we basically use parallelization in order to reduce the latency. And in fact, this is, I think, one of the only instances in proving verification where we can actually simultaneously both reduce latency and reduce cost. Typically, they're traded off between each other. Another interesting thing in recursion is, in fact, if you think of the recursive tree, we actually have a notion of off-chain proofs. So basically, not all proofs reach the blockchain. We don't, or reach the underlying layer. And off-chain proofs can be combined together in very interesting ways. Today, basically, we just combine proofs and eventually get the same effect on chain. But we could combine proofs and also combine their outputs. And in that way, let's say you have a transition from A to B and another transition from B to C, two state transitions that are proven by two different proofs. You could submit a third proof, and these could be proven off-chain, and then you could submit the third proof proving the transition directly from A to C without ever submitting on-chain a transition from A to B. And that notion can be extended to all kinds of applicative recursion notions, and reducing even further the on-chain footprint, such as data availability on-chain and things like that. And finally, there are also benefits in terms of implementation, and we're talking about layer 3s, so let's move on to that. So I wanted to show you this picture of this wonderful cake. Layer 3s are like a wonderful cake. So technically speaking, layer 3 just extends the same notion of layering that layer 2 introduced. Layer 3 looks at layer 2 exactly like layer 2 looked at layer 1. So basically, the app goes up one layer. we prove the correctness of state transitions on layer 3 to layer 2. We don't care about layer 1. Layer 1 is abstracted away from layer 3. So we just prove to layer 2. It implies that we need a verifier in layer 2. But assuming we have a verifier in layer 2, and the recursive verifier that we talked about before could also be deployed as a StarkNet contract. So we have a verifier in layer 2. Then we can prove to layer 2, the underlying layer, that we have a valid state transition, and we can track that state of layer 3 on layer 2. So that's the basic idea. So what is that good for? So we talked about the benefits and drawbacks of layer 1. We talked about the benefits and drawbacks of layer 2. And likewise, we can talk about the benefits and drawbacks of layer 3. So of course, I think the first thing that people say, wow, now if layer 2 scaled layer 1, now layer 3 will scale layer 2. Yes, super scalability is wonderful. That means it's possibly faster, it's possibly less costly. Of course, that depends on what you put on the layer 3. If everyone were to move to layer 3 and layer 2 wouldn't have anything to do but verify proofs from layer 3, then you wouldn't get better performance from layer 3 than you would get from layer 2. The whole idea is that you may have multiple layer 3s on top of a single public layer 2, for instance, and all of these aggregated together would give you higher performance, okay? Similarly to what we do today with multiple layer 2s on layer 1. So that's another scaling factor in terms of performance. And of course, you get the lower cost, because now, and that's quite trivial in a sense, you do all your computation on layer 3, and layer 2 now even needs to work less, and of course layer 1 doesn't even see many of the proofs. And we keep security. So it's as secure as layer 1, or as secure as layer 2, I should say, because layer 1 is abstracted away. And eventually you get the security from layer 1 through the layer 2 that relies on layer 1. And the new thing in layer 3s is that the onboarding and offboarding between layer 3 and layer 2 are much less costly than the relationship between layer 2 and layer 1, because they're governed by the cost of layer 2. And since layer 2 is already a low-cost platform, you get low-cost on- and offboarding from layer 3, which implies you get better interoperability between the app running on layer 3 and everything happening on layer 2. And it's not composability like you would possibly want. And if you want composability, you need to be on the same platform, on the same layer together with other apps. But low-cost interoperability is certainly a big benefit of layer 3. And again, layer 3 could be public networks, could be private apps, could be application optimized, and in particular, if they're not public, they could be uncongested, deterministic performance, and that's one of the things that are very, very interesting in this context. But could be also the same technology as layer 2. So you could have a layer 3 StarkNet that's used for a specific app on top of a public layer 2 StarkNet, and the layer 3 StarkNet could be public or could be private, so you can recursively build all your applications. And here are just a few examples of what you can achieve with a layer 3, and some of these examples are actually work in progress by some of our customers. Superscaling, obviously, that's the kind of the almost trivial example. We're currently actively building StarkX layer 3, which means StarkX that will be able to run on top of StarkNet. You get an app optimized for exchanges, perpetual or spot trading, and you get the benefit of reduced on- and offboarding. We talked about that. You could have a customized layer 3, StarkNet, for a specific Cairo app. The whole idea here would be to have like an application that is congestion-free, has deterministic costs, low-cost interoperability through onboarding and offboarding, and public access. So it's still a StarkNet. But on the other hand, you may have more control about what you deploy on this StarkNet, because it's not a public StarkNet. And in this kind of environment, you could run an app that's sensitive to, for instance, performance latencies and things like that. Another kind of layer 3s is for compute offload. So it doesn't have to be a network, doesn't have to be a layer. Let's say you have complicated gaming logic and you want to run that outside of your blockchain. You can run it as a layer 3, submit proofs to layer 2. Layer 2 can verify those proofs, get offloading. And finally, privacy. In a private environment, you can create your own proof, submit that proof to layer 2, and you get the data that you want to layer 2 from that layer 3 for privacy. So in the diagram, this is something that some way to depict it. It's a layered approach, layer 1, layer 2, all kinds of layer 3s, some of them app optimized, some of them public, some of them private, and maybe even a layer 4 in some cases and beyond. So I hope you're persuaded that the different solutions, the different layers, the different ways to use these layers will satisfy your appetite, at least for now. Eventually, it'll get congested. So thank you very much. And I believe I have 1 minute left for questions. Yes, please.
So why stopping at L4? Why not L5?
Okay, this is a question I always get. Why stop at L4, not L5, L6? Okay. You don't have to stop. It's just a matter of if you gain a benefit or not, right? So why did I mention L4? Maybe you have a public layer 3 on top of which you have an uncongested environment where you run your application, but you want to add privacy to that. Since it's a public network, you can't do privacy there, so maybe put the privacy on top. If you have another, I don't know, application that on top of privacy wants to do, I don't know, something else, then maybe you'll build a layer 5. I didn't think of an example yet, so you don't have to stop there. Yeah.
How does EIP 4844 impact or change anything that's going on in the StarkWare system?
The question is, how does EIP 4844 impact? 4844, just in a word, is about data, basically transmission and basically how you track storage on the layer above, on layer 2, on top of layer 1. Okay, so typically today in rollups, and this is also how StarkNet works today, you send all the state changes as transmission to Ethereum. And that costs. It'll cost less with 4844, so it will be more effective. In fact, StarkNet is also going in another direction. Previous talk was also mentioned here. We'll also have off-chain data availability on StarkNet. So in those cases, it won't affect. It's a possibility. We'll support multiple data availability solutions in StarkNet. And in particular, any layer will benefit from that. So